All right, homework for nonlinear regressions. We're going to need Desmos for this too. So at the end of 2005, Marissa placed $750 into an account, but then made no other deposits and so on. The table below shows the balance of the account at the end of each year, beginning with the initial deposit. Use exponential growth or exponential regression. So that's what this is. So we're going to use this model to represent that table and then answer the question after that. So let's go to Desmos right now. And we're going to click on table, and then we're going to put it in. Now, I'm going to put in 0, 1, 2, 3, 4 for the years instead of 1990, 2005, and so on. And then we have $750, no dollar sign, $794.79, 842.25, 892.54, and then 945.84. All right, I'd like to actually see the graph here, so click on the wrench, and we'll change the scale. So I'm going to change this scale from 0 to 10 is fine. I'm going to change this scale so it goes 0 to, well, what do we got? How about 1100, something like that, so that I can then see the graph in front of me. So do you see the points here that we're working with? And then underneath we'll do a regression. So we're going to type y1 and then this weird kind of sideways approximate sign, and then it's ab to the exponent x1. So there is a linear exponential regression, and you can see r squared is equal to 1. That means it's like a perfect match. So that's great. A is 750, so I'm going to write that down. And then the base is 1.06, I'll round to the exponent x. So now I have that. The next question is, find the year in which her balance is $2,000. So $2,000 is the y value. So type in the y value is equal to 2,000. Oops. And then I got to move the graph until I see the lines intersect. So 2,000, there's the red line. Keep moving until you actually see them intersect. And then right there, so at 2,000, how many years would that take? And you have your answer. So about 17 years later. Then we still have to think just a little bit. So we solve this. X is equal to about 17. And then this is where we started. So I have to go 17 plus 2005. So in the year, Adam, was that 2022? The balance will reach $2,000. Done. All right, story number 2. The table below shows the annual sales of a company in thousands of dollars. In each of its 6 years, use a power regression. So it's similar, but x and then to the exponent b. That's what we're going to use. So we're going to type this into Desmos. So let's create a fresh table. We're going to type these in. 1, 2, 3, 4, 5, 6. And then 157, 238, 304, 361, 412, and 460. Then a power regression. Again, I like seeing it here on the right. So I'm going to change the scale. I don't need to change let me change this. So we'll go 0 to whatever, 6, so like 0 to 10. here on the y-axis, we'll go 0, 460. What is that? Like 600 maybe? Here. So now I can see the points here. So now let's do a regression. So y1 and that sideways whatever, a x1 to the exponent b, and then look and see, again, what a great r squared value. Can't get better than positive 1. There it is. So I'm going to use a. I'm going to write it down. So a is 157, and then the exponent is 0.6. So what a great model for what's happening. Now the question is, find the sales of the company in the 10th year. Well, the year is x. So if x is 10, what's the answer? So I'm going to go to x equals 10. And then right here, what's the sales going to be in year 10? And you have the answer. So 620, we'll round it to 25. And that's in thousands of dollars. And then a simple sentence. Oops, I didn't mean to hit podcast. Here we go. Let's see if a podcast pops up. So the answer is, in its 10th year, the sales of the company should be 625,000 because it's in thousands. All right, number 3. The table below shows average United States life expectancy in years since 1900. Use a logistic regression to write an equation to model the data. So this would be 1910 all the way up to 2014. So if this is since 1900, let's have an understanding of this, and let's use this in a logistic growth model. Looks like this. And we're going to use that when we type it in. All right, let's clean this up. New table. And let's type it in. So it's 10, 20, 30, 40. The more data we have, the more accurate the model. Data is very valuable. That's the Google idea, right? And keeping things private, and how much money data is to a company to be able to have the best model they can. They love your data. Though internet's all about that, and it is extremely valuable. So the more data you have, the better your model, the more money you're going to make. Okay, so there it is. If I change this scale, let me change this to 0 to like 100. Change this scale from 0 to, I don't know, let's say 90, right? It's not going to be much more than that. And then, so you can see the points here. We'll do a logistic growth model. So y1 and that, and then divide. So C1 plus A, E, and then the exponent negative BX1. So you can see the logistic growth model there in terms of what we're looking at. And it has a good R-squared score. So let's use that. So the equation then would be 83 would be the max, right? Caps out at 83. And then 1 plus A, that's 0.87. E, B is negative 0.03. X. So there's the logistic growth model. And then the question is, what's in 2014? So that's 114 years later. So X equals 114. So at 114 years later, What's the life expectancy? And the answer is about 80. So at 114, it's about 80. Why 114? So from 1900 to 2014 is 114 years. Notice the cap in terms of life expectancy is 83. So the expected life expectancy in 2014 should be 80 years, which is well up from 50 years in 1910. 30 more years of fun. Turn the page. What's this story about? So there's a group of foxes. That's called a skulk, if you ever knew that or cared or probably don't. So a skulk of foxes. The table below shows the population of the foxes since 1996. Use a logarithmic regression. That's what it looks like. To write an equation to model this data and then answer a question. So that's the model we're going to use. We're going to, again, delete what we did before. We're going to create a table. We're going to fill in the table. So 1, 2, 3, 4, 5. And then the fox population went 87 to 116 to 131 to 145 to 154. To see it on the graph, we're going from 0 to like 10, let's say. And then on the y-axis, it's like 0 to, let's say, 300. So there you see the picture right there of the points. So a model, y1, squiggly, a plus b ln x1. And then again, look how good a model that is. 0.999, like perfect, really. And then use those numbers for your equation. So a is 86 plus b is like 42. And you have an equation. And then with that equation that's already in Desmos, how long would it take the population to reach 200? That's the y value. So y equals 200. Where would that be? So you're looking to see where they intersect. So 200, how many years would that be? In about 15 years. And then write a sentence. So in about 15 years. All right, we got 3 more stories today. All right. Next table. The table below shows the height of a tree in inches during the first 6 years. Logistic regression. So a logistic regression, again, is this one. The more times you write it down, the more you remember it. And we're going to use this. Now, we have the year and we have the population. Why is it the population? So first, this is the height. I think. The table below shows the height of a tree in inches during that, and then when will it reach a height of 9 feet? So this is height, just a typo, in inches. So that should have said height in inches. Know that 9 feet times 12 is what, 108? Is that how you spell it? Write it out. That's 108 inches, just so you know. So that's what we're looking at when this number is 108. All right, let's put that in. So we got year 1, 2, 3, 4, 5, 6. More data, the more accurate the model. And then 37.1, 41.9, oops, 48.7, 60.2, 68.4, and 75.5. And then we're going to go Y1, and we're going to put in this logistic one, which is C over 1 plus A e to the exponent negative B x1. And then recognize it's a pretty good model in terms of it. And there's my points. And then I'm looking for how long it will take the cobra to reach, no, the tree. The cobra is the next question. That sounds fun. The height, y. So when y equals 108, how long that would take? Here it is. And the answer is about 10. So let's write a sentence on that. So in year 10, the tree will be about, what, 9 feet tall. All right, you got 2 sentences left. I got excited about Cobra. So the table below, do you watch Cobra Kai? Probably don't know what that is. All right, the table below shows the length of a cobra in inches for the first 5 years of its life. Determine which model is a better model for this. So age, length of the cobra, which sounds so cool. And then we're going to type this into Desmos. And we're looking for the R-squared score that's closest to positive 1. That's the better model. Here we go. So first the table. Next, the length of the cobra. And then do a logistic. What do they say? 2. One's a logarithmic. So this is logarithmic. So, and then look at the R-squared score. And then the other one, we'll do a second one. And then look at the R-squared score, and whichever one's better. Exponential would be AB to the exponent x1. And you can see that R-squared score is worse. It's less, like it's further away from positive 1. Get rid of it, not the better one. So the logarithmic one's best. And then to use that one, when will it reach 90 inches? That's what y is. So when does y equal 90? And you have your answer. So the model we're going to use is this. F at x equals A. Move my head. Is 13.82, so like 14. B is 35. We're just rounding. And then, when will it reach? And the answer is about 8.5, right? So at what age? At 8.5 years old. The cobra will be, how many? 90 inches long. Wow. That's long. I don't want that really as a pet. All right. I don't know if you're even allowed to have that as a pet. So 8.5 years old, the cobra will be 90 inches long. So you have your function. We made the function equal to 90. We solved it at about 8.5. So at 8.5 years old, the cobra will be 90 inches long. We got one story left. I'm annoyed with my head. I don't know how to get my head out of here. So the table below shows the number of smartphone owners. So we have the years and the users in millions. So let's type this table in. You know the drill by now. So let's get that table in. And so the table has 1, 2, 3, 4, 5, 6. And then on the other side we have 1.6, 7.1, 18.2, 33.9, 52.7, and 85.8. So one model will be an exponential. Get my head out of there again. Oops. Let's try that again. Exponential. Get that. There it is. There it is. And so you get 0.9. That looks like a good model. A power function, maybe it's better. Let's see. So a power function will have x1 as the base, and the exponent is b. 0.997, 0.990. Interesting. Well, 0.997 is better. So get rid of this one. So there's a better model because it's closer to 1. And then the question is 2028. So the first year since 2020, 2010, so 2028 is 18 years later. So we have to go x equals 18 and then figure out where that is on the graph. And then how many is that? So let's write the equation down and then solve it in terms of the question. So the equation as a power is f of x equals a is 1.3 x, and then the exponent on x is 2.3. So there's the power function. In 18 years, make it equal, plug in 18. And if you plug in 18, you get 1,072. Let's make sense of this and write a sentence. So there it is, 1,000. So let me just see here. All right, just hold on 1 second, okay? Honey? Okay. All right, we're almost done here. Sorry about that. So let's write a sentence here. So determine whether that, so we determined it was a power function. There it is. There's the answer. And this is in millions. So we have to add 1, 2, 3, 1, 2, 3 to have a sense of 1 trillion in terms of 2028. So in 2028, 1 trillion. No, sorry, trillion. What's after million? Billion. 1 billion, 72 million. See if I know my numbers. Will own smartphones. I don't doubt it. Hey, you just did your homework. I'm so proud of you, Mr. G Math, over and out. Until next time.